Hello everyone. In this video, we will be discussing about dynamic stiffness method. So, which is the part of module 5. Uh, Related to that, we have some derivations and we don't have any problems again numericals, but we have some derivations. First, we will discuss the concept of this dynamic stiffness method. Then it will be easy for us to understand the derivations. So, the mass distribution of the element is treated in an exact manner in deriving the element dynamic stiffness matrix. The dynamic stiffness matrix of one-dimensional structural elements, taking into account the effects of flexure, torsion, axial and shear deformation, and damping, is exactly determinable, which in turn enables the exact vibration analysis by an inversion of the global dynamic stiffness matrix. The method does not employ eigenfunction expansion and consequently a major step of the traditional finite element analysis, namely the determination of natural frequencies and mode shapes, is eliminated, which automatically avoids the errors due to series truncation. Since modal expansion is not employed and HOC assumptions concerning the damping matrix being proportional to the mass and stiffness are not necessary. The method is essentially a frequency domain approach suitable for steady state harmonic or stationary random excitation problems. The static stiffness matrix and the consistent mass matrix appears as the first two terms in the Taylor expansion of the dynamic stiffness matrix with the frequency parameter. So here we have to be knowing the basics of the modal analysis and even the harmonic analysis for both the harmonic conditions. So far, the dynamic finite element method has been applied to classical local systems only. Now, we generalize this approach to non-local systems. One of the novel features of this analysis is the employment of frequency-dependent complex non-local shape functions for damped systems. This in turn enables us to obtain the element stiffness matrix using the usual weak form of the finite element method. First, we introduce the equation of motion of axial vibration of undamped and damped rods. Natural frequencies and their asymptotic behaviors for both cases are discussed for different boundary conditions. The conventional and the dynamic finite element method are developed. Closed form expressions are derived for the mass and the stiffness matrices. The proposed methodology is applied to a armchair single-walled carbon nanotube. In short form, it is called as SWCNT for illustration. Theoretical results, including the asymptotic behaviors of the natural frequencies, are numerically illustrated in the coming slides. And this is the axial vibration of a single-walled carbon nanotube. And you can able to see this. This is a zigzag SWCCNT 7,0, and this is the carbon atoms. So you can able to see this when it is clamped. Correctly speaking, this particular rod, non-local nanorod, was clamped. Left side is fixed freely, and we try to move this in both the plus x direction and minus x directions. So because of this, what happens? You can able to see here that there will be a zigzag movement of the carbon atoms. The same thing only was explained here. That is, first the natural frequencies and the asymptotic behaviors for both the cases are discussed for different boundary conditions. So what is the different boundary condition mean? The first boundary condition is it is fixed here and it is moving in both minus x direction plus x direction. And what is the second asymptotic condition is required again for the same cantilever and non-local nanorod, where a point load is applied from the top, and even second condition is a point load is applying from the bottom towards upwards. So plus y direction and minus y direction. So and for the experimentation purpose, we will be considering a small portions, and the small portion microscopic view only we are seeing here, where you can able to see here the small portions where the zigzag movement of the carbon atoms can be clearly seen here. And next one, the conventional and the dynamic finite element methods are developed. So we will be finding out both the conventional method and dynamic finite element method. Conventional method means where starting from the static condition where gradually the load is applied, starting from that condition and even to the dynamic finite conditions, where as of a sudden we will be applying a certain amount of the load. So we will be comparing both the conventional condition and the dynamic conditions by using finite element methods, and we will be comparing the results for both the cases. So the closed form expressions are also derived for the mass and the stiffness matrix conditions. And we have some of the examples in our laboratory where we will be discussing about modal analysis and harmonic analysis, where in the modal analysis again a cantilever beam only will be taking, but instead of these kind of loading condition we will be considering a point load which is acting in the y direction. I mean the direction can be plus or minus, but in the y direction only we will be applying, and accordingly we will be finding out what is the mode shapes of button, and we will be keep on changing the magnitude of the load applied. So if you keep on changing means what happens, even there will be a change of the frequency, and that comparison also will be showing up. And moving to the harmonic analysis, where we will be doing a graphical chart. So in the chart we can able to see that the harmonical behavior, that is at which point or the which node the maximum frequency or the maximum amplitude has been experiencing. So that also will be checking with the help of a harmonic in the harmonic analysis. So both the modal analysis and the harmonic analysis we will be doing in the lab. So theoretically we are not doing any kind of derivation for the modal and harmonic. This is the basics we are learning here.